Welcome back to Chemistry Part 2. Now we're going to go through inorganic and organic compounds. Inorganic compounds generally don't have carbons. They're simple molecules, just a couple atoms, whereas organic compounds have a carbon backbone, and they have covalent bonds between the carbons and hydrogens in there. First, we'll look at inorganic compounds. Water is the most important inorganic compound. Its structure allows life to exist. If there was another planet with life and it didn't have water, their structures would have to be totally different. All of ours is based on how everything reacts with water. So we've looked at its structure a little bit in Part 1, but you've got an oxygen and two hydrogens sharing electrons. So they're forming covalent bonds, but they're unequal. So the oxygen is the electron hog. It's slightly negative, which means the electrons are more likely over here. Since they're more likely over here, the hydrogen is going to be slightly positive. That makes water polar. It's got a charge. It dissolves polar molecules. It does not dissolve nonpolar molecules. So like lipids, fats, they don't dissolve in water. And we use that to our advantage when we want to separate different areas of water. We'll use fats. It is the universal solvent. Things dissolve in it. I like it. It's a funny joke. Okay. So here's an example of showing it as a solvent. You have table salt, and when it gets in water, it dissolves. They dissociate, the molecules separate. You've got your positive sodium, and it's surrounded by negatively charged oxygens. You've got your negative chlorine, and it's surrounded by the positive hydrogens. So it dissolves salt. Also, it's a really great thing to have water for reactions. When we do reactions, we do what's called dehydration synthesis or hydrolysis. So dehydration synthesis, that's building bonds. Synthesis is making. Dehydration, we make the bonds by taking out a water. We remove this, and then they come together. Whereas hydrolysis, water breaking down. We break bonds by inserting water. Water's thermal capacities. Water has a high heat capacity. So what that means is that water changes temperature very slowly. You have to put a lot of energy in to change water by 1 degree. That's important for our bodies. If our body temperature was able to change very quickly, if it had a low heat capacity, we would have a terrible time regulating it. So like metal changes temperature really fast. If you put a pot on to boil water, turn it on high and touch it in 2 minutes, the metal will be really hot and can burn you, but the water will still be cold. And then it also has a high heat of vaporization. So what that means is when water evaporates, it takes a lot of energy. It takes a lot of heat. So we can use that to our advantage with sweating. When you sweat and the water evaporates, it helps cool you off. That's why when it's really humid outside, it feels hotter, because you're not being able to cool down with the evaporation. Next, water as a lubricant. It helps reduce friction in our body. We've got serous membranes where it helps reduce friction around our heart, our lungs, and our abdominal pelvic region. And then we've got it like in our joints. So here's a synovial joint, like your knee joint, your elbow, your fingers, any movable joint. And you've got this space inside there filled with synovial fluid. That's mostly water. It's got some proteins in there too. And that helps the bones slide over each other more, so you don't have this cartilage getting broken down and you don't have the bone getting broken down. Now let's look at the 3 different types of mixtures that we can make. When we put these compounds together physically, like we mix them up, but they don't have chemical bonds. You've got solutions, colloids, and suspensions. So a solution, like an example, table salt, salt water, is where you have this solvent, like the water, and things dissolved in it, the solutes. And when those are together, it's called a solution. It's homogeneous, so it's the same throughout the whole thing. Like if you were to drink salt water from the ocean, it's homogeneous. It's the same all throughout. Suspension is a mixture where things are physically mixed together, But if you leave it sitting out, they separate. It's considered non-homogeneous, so oftentimes you'll have like big pieces of something in the solution. So you'll have big pieces of flour in there. So some parts are going to be flour, some are going to be water. They're heterogeneous. They're not homogeneous. And if this was to sit here, the flour would sink down and the water would rise to the top. So that's an example, would be like blood. Blood, if you sit it out, the red blood cells are going to sink to the bottom. The lighter blood plasma is going to be at the top. And the last is a colloid. So a colloid, it shows us milk. If you leave milk sitting out, it's still going to be milk. It's going to stay mixed up, even though, like the suspension, it's heterogeneous. There's different parts, like fat versus water. Like if you have Jell-O sitting out, the Jell-O doesn't separate. An example of this in our body would be your cytosol, the part inside your cell that's like fluid and all the different organelles, all the pieces working. Next, we're going to look at acids, bases, and salts, and this can get really confusing. An acid is anything that, when put in a solution, adds hydrogen molecules. So what hydrochloric acid does is when it goes into the water, it separates into H plus and Cl minus. It increases the amount of hydrogen ions. And where that goes is it adds to water. So if you've got H2O and you add an H plus, that gives you H3O plus. So some will be water still, but for every hydrogen ion you'll add, you'll make an H3O plus. Bases do the opposite. They take out hydrogen ions. So this is potassium hydroxide, and it's a very strong base. So what happens when it gets into water is it separates into the potassium and the OH minus. So here, if you compare it to water, this is subtracting an H plus. So H2O minus an H plus is OH minus. So bases reduce the amount of hydrogen ions. Now you're going to have some water and some OH minus. And then a salt is neither an acid or a base. And when it separates out into its parts in water, it doesn't change the pH. But it does dissolve, it does dissociate, it does come apart into its different portions. Let's look at the pH scale now. So we talked about what makes something an acid and what makes it a base. And we measure how acidic or basic something is with the pH scale. 7 is neutral. That's water. Our OH minus equals our H plus, we've got H2O. And as you add more H pluses, you get more and more acidic. So like a pH of 2 is really acidic. Stomach acid is pH of 2. It's got a lot of H pluses, less OH minuses. And then going the other way from neutral, if you take out the H plus, if you add in more OH minus, your pH increases, you become more basic. In our body, it's very important to maintain a normal level of pH, to maintain pH homeostasis. If we change too much, it can affect our proteins and they can unfold and denature. It can damage our linings of our organs. It's very important to maintain normal levels. What we have in our body for quick fixes are buffers. Buffers are weak acids or weak bases that change based on what's been added to the solution. So what happens is, let's say you add in a lot of H pluses. What would happen would be, if there's not a buffer, pH would drop. But if you have a buffer, what happens is the buffer picks up that hydrogen ion and pulls it out of the solution, so it doesn't change the pH at all. And if a base is added, if a lot of OH minus is added, it drops off the hydrogen, so that can go back with the OH minus and make more water. So this is a very quick, short-term fix. If we want to change our pH levels more long-term, we'd use our respiratory system and our breathing rates, as well as our urinary system to either get rid of more hydrogen ions in our urine or less. Let's get into the organic molecules now. They have carbon backbones. Carbon, because it makes 4 bonds, can make really complex molecules, and we use all 4 different types for our body. First, you have carbohydrates or sugars. They are for our energy. They help us mark the outside of our cell. We're going to look at multiple different types. First, you have monosaccharides. Mono means one, so one sugar, single sugars. So for example, in like DNA and RNA, we'll look at deoxyribose and ribose. And then like glucose, fructose, galactose, those are all hexoses. That means they have 6 carbons. Our body can only absorb individual sugars. Disaccharides, di means 2. These are sugars with 2 parts. So this first one we have is lactose. It's a really neat one. So what happens when we drink milk and we have lactose, what our body generally does is it breaks this bond. So we absorb both of these into our body. But for people who are lactose intolerant, they can't break that bond. So this doesn't get absorbed into our body and it stays in the intestines. And when it gets to the large intestine, the bacteria there then use it. And they make lots of products, including gases, that can be sulfur-based. So that's why you have all those cramping, gases, if you're lactose intolerant and you have lots of lactose. And last we have polysaccharides. Poly means many. So what you have here are these individual monomers, these monosaccharides that have been bonded together. Polysaccharides are the storage form. In animals, in our bodies, we store it as glycogen. Plants store it as starch. Also cellulose, which is woody, and our bodies can't break that down. Like termites have special bacteria that break it down for them. The next type of organic molecule we're going to look at are lipids. So lipids are fats. Fats don't dissolve well in water. We use that property to our advantage when we have them be part of our cell membranes. We also use them for energy. First are fatty acids. Fatty acids are considered kind of the building block of lipids. You've got these long carbon chains, and they're either very straight, they only have single bonds, or they've got some double bonds and they kink. So the ones that are very straight are saturated. These carbons are saturated with hydrogens. They don't have any double bonds. So when you've got lots of saturated fats, they're solid at room temperature because you can have 1, 2, they can stack really nicely. Unsaturated fats have double bonds and they kink. They don't fit nicely together, so there's more spaces. They're oil at room temperature. Next, triglycerides, they're protection, insulation, energy. So we store our fats generally as triglycerides. And when you've got your fat cells, they provide protection and insulation, so they cushion our organs. They provide insulation so we can keep in heat better, and then we can break them down for energy. So we've got a backbone with 3 fatty acids hanging off. Next, phospholipids. So phospholipids have a polar head and nonpolar tails. That means the polar head likes water, it dissolves in it. The nonpolar fatty tails don't. We use that for our cell membranes. These are the outside of our cells. So you've got a double layer, a bilayer of phospholipids. You've got the polar heads on one side, so like this would be the outside of the cell. And you've got in the middle, the nonpolar tails next to each other. And on the inside of the cell. Then you've got steroids. These are all derivatives of cholesterol. Instead of being long chain fats, they're ring structured. Examples of those would be hormones. So testosterone, estrogen, sex hormones, and then cortisol, like glucocorticosteroids, like stress hormones.